You know, if you've ever stared at a stock chart, you get this feeling that it has a mind of its own, right? One day it's just ticking along, the next it's rocketing up, and then, out of nowhere, it just nosedives. For a long, long time, financial models tried to team this beast with some really elegant, but honestly way too simple math. They were missing something, a kind of ghost in the machine. So today, we're going to dive into the new math that's finally starting to capture the market's memory and its wild mood swings.
Okay, so let's get right into it. The first thing we really need to wrap our heads around is why the old models just weren't cutting it. They were basically haunted by things happening in the real world that they just couldn't explain.
And this question, this one right here, it gets to the absolute heart of the problem. You see, classical finance is built on this idea that the future only depends on where we are right now, not the past. But what if that's just flat out wrong? What if markets actually remember what happened yesterday and the day before that? I mean, this slide really lays it all out. On the left, you've got this neat and tidy world of the classic models. Smooth, predictable lines where the past is forgotten in an instant. And on the right, well, you've got reality. Jagged, chaotic paths where a trend can keep going, and then bam, a sudden shock, a huge jump from some unexpected news. These two things, this long memory and these sudden jumps, these are the ghosts the old models just couldn't see. So if you want to see these ghosts, you're going to need a new language, a totally new set of mathematical tools that are built from the ground up to describe a world that has both memory and shocks. So the first piece of this new language is something called fractional Brownian motion. The key idea here is this thing called the Hurst exponent, or h. When h is bigger than a half, it means if the market was trending up, it's just a little bit more likely to keep trending up. The coastline analogy is just perfect. The shape of the coast at any one point isn't totally random, right? It's connected to the path it took to get there. That's market memory, right there in a nutshell. And the second part of our language? Well, that deals with the shocks. Jump processes basically let a price teleport. I mean, 1 second it's here, and the next, after some huge news hits, it's just somewhere else entirely. It doesn't even travel the path in between. And that captures the brutal reality of a market crash or a sudden rally perfectly. Okay, so let's actually build a sentence in this new language, piece by piece. It all starts with the simplest part, the drift. This first term here, you can think of it as the predictable bit, the gentle, underlying current of the river, the average direction we kind of expect the market to go over time. All right, next up, we add the memory. The second part, the one that uses our fractional Brownian motion, introduces those persistent wiggles. This is the math that represents the market's memory, making sure that the path it takes is influenced by everything that came before. It's not just a random walk anymore. It's a walk that remembers where it's been. And finally, the shocks. This last term is our teleportation device. It's what accounts for those instant, jarring leaps we see when something big happens. And just like that, we have the whole shebang in one place, a single, powerful equation that can describe a market with a trend, a memory, and sudden mood swings. But there's always a catch, isn't there? This beautiful equation is so complex, it's pretty much impossible to solve with just a pen and paper. So if we can't solve it the old-fashioned way, how in the world do we actually use it? And that brings us to the next chapter in this story. If we can't solve the equation on paper, well, we're going to have to build it piece by tiny piece using a computer. The answer is simulation. Instead of trying to find one single grand formula that describes the market's future, we use computers to simulate thousands, maybe even millions of possible paths the market could take, one tiny step at a time. And here's basically how that works. You start with today's price. Then you calculate the tiny little push from that average trend. After that, you add a wiggle that remembers where it came from. Then you roll the dice to see if a big shock happens. You land on a new price a fraction of a second later. And then you just do it all over again, thousands and thousands of times, to trace out one possible future. Okay, but how do we know these computer simulations are actually any good? Well, this graph is the proof. It shows the simulation's error compared to how small we make our time steps. And look, as we make the steps smaller and smaller, which takes more computer power, the arrow goes down in a perfectly predictable way. That straight line is just beautiful evidence that our method is reliably closing in on the right answer. And this wasn't a fluke. Here's a totally different way to run the simulation, and what do you know? We get the same result. The error shrinks predictably. This tells us our approach is robust. We can actually be confident that these computer simulations are giving us a faithful picture of the complicated world our equation describes. So we have this powerful new language, and we have a way to make it talk. But what's the point? Why does any of this actually matter? Well, at the end of the day, it's all about getting better at pricing real-world risk.
This number, right here, is the bottom line. When they tested this new model against real data from the S&P 500, its average error when pricing financial options was just 1.9%. The classic model it replaced, its error was 5.4%. I mean, this new approach isn't just a little better, it's almost 3 times more accurate. And that's not just some academic victory. That's a huge deal for understanding risk, which affects everything from your retirement account to the stability of the entire global economy.
And this is what it looks like in practice. This curve shows the prices the model spits out for a financial option across a bunch of different scenarios. This isn't just theory, it's a tool that creates realistic prices that actually reflect the market's true, messy nature. For a trader or a big investment fund, having prices that are this close to reality is a massive, massive advantage.
You know, one of the biggest wins for this whole approach is that it can finally explain something called the volatility smile. It's this weird pattern you see in the real world where certain options are way more expensive than the old models would predict, creating a smile shape on a graph. For decades, this drove people crazy because the classic models just couldn't replicate it. But by adding in memory and jumps, this new model nails it.
So let's just do a quick recap. Real markets have ghosts. They remember the past, and they have sudden shocks. We've built a whole new kind of math to finally see them. And because this math is so complex, we have to use powerful computer simulations to figure it out. But the result of all that work is a dramatically more accurate way to model our financial world and price the risks inside. And that leaves us with a really fascinating final thought. We've built these incredible tools to model systems with memory and shocks inside of finance, but where else could we use them? Think about climate patterns, or how diseases spread, or even the wild, unpredictable path of human behavior. The kind of jagged, patterned chaos they describe isn't only in the markets. What other ghosts in what other machines might we finally be able to see?